The format for this afternoon is that we will hear from each of our two competitors. Questions during the talk, please. And at the end of the talk, each judge is allowed one question. We'll hear James Barmer first and then Peter Taylor. When we've heard both the competitors and the judges have asked their questions, I will then close this session. The judges and I will then have a private session to deliberate over the results, and I will let people know. Obviously, I'll let the contestants know directly as soon as we've come to a decision, and then the result in general will be, I'll circulate it round our newsletter. It will also be on LinkedIn and our Facebook page, and I'll put it on our website as well if I can get it on. So that's going to be the modus operandi. Judges, you should have marking forms, which I have sent to you. I would like you to email these to me after the event. During the event, during the judging session, we'll combine our scores to work out a winner, but I do need the final sheets for our records. I will be the timekeeper. I have a stopwatch here, so I will be recording the time that you both take. And as you're aware, there are penalties for overrunning. They seem the rules, and there are no penalties for underrunning, which is different from last time, but never mind. So I think that's all I need to say to start off with. Does anybody have any questions about anything before we kick off? No? Okay then. Right. Just let me find James. Right. I'm just making you presenter, James.
Thank you.
Right. James is now the presenter. So if the rest of us, if we're not already muted, can mute ourselves. And I'm ready here with the buttons. So
yes,
if you'd like to get your screen up first.
Of course, please just let me know when you see it.
Yes, we won't deduct this from your time, obviously, because
I was hoping that you wouldn't.
Just right, that's got the lead slide on for me.
Excellent. So, okay.
So whenever you start, over to you, James.
Yes, all right. Okay, so my name's James Barmer. I'm a process engineer with Prime Metals Technologies Limited, and today I'm going to be presenting a case study of working on site in India. So, during the course of this presentation, I'm going to describe to you the challenges that I faced and overcame as Prime Metals' sole representative on site during this period. The site in question is JSW Dolvi in Maharashtra state, India, not too far outside of Mumbai. The scope of work for the project was the installation of a new cyclone dedusting vessel to replace the old vessel, and when I say old, it was 2 years in service, which was suffering from quite extensive abrasion and leaks of gas. My responsibilities on site were overseeing the mechanical and refractory installation, as well as then commissioning the equipment that was installed. The key challenges on this site can be summarized as safe working conditions on site, adverse weather, and then the need to commission during an active construction phase, all of which I will go into greater detail during the presentation. For a little bit of background information, this is the site that we were working on, or the area we were working on within the site, rather. You can see there that the red coloured sections were the existing cyclone that was being removed and the existing pipework into that cyclone. The green section was equipment, new equipment installed by Prime Metals that was going into place before the shutdown period, and then the blue would be placed during the shutdown period. The reasoning behind doing it in this method was to reduce the amount of work that would need to be done during the shutdown itself to minimize any potential overruns. So the project, for me, was split into 3 primary phases, the latter 2 of which will be explained in greater detail, but just quickly to summarize. Phase 1 was the design. This was done primarily entirely within the office. I took client operating data that the customer had provided to Primetals and used that to size the cyclone dedusting vessel and all the associated equipment and mains. Phase 2 was the overseeing of mechanical and refractory installation on site. I was required to be on site for this period, as the refractory material itself was a guaranteed item for terms of the contract that Primetals signed. Phase 3 was the shutdown and commissioning. So all of the pre-shutdown preparations, the shutdown itself and all the associated work, and then post-shutdown checks and commissioning. For those of you who aren't aware of what a cyclone vessel is, I'm just going to quickly describe it now. So you see on screen there a cyclone dedusting vessel. It's a computational fluid dynamic diagram of the gas flow within the cyclone and entering and exiting. The concept behind it is that the gas enters tangentially to the cyclone itself, imparting a rotation upon the gas, which then, through centrifugal force, causes the dust entrained within the gas to impact into the side of the vessel. This dust loses velocity, falls to the bottom of the cyclone, and is then collected in the dust storage area directly below. The gas stream, with smaller entrained particles still contained within, is then taken out of the exiting main into a wet scrubber system. Now, phase 2. Phase 2 consisted of overseeing of the mechanical installation, primarily for me that being the backing mesh that you can see in the picture there. That backing mesh was supplied in 2x1 meter sections, required manhandling inside the cyclone body through a relatively restricted access point, and then manhandling within the cyclone into position for it to be welded in place. Secondarily, refractory installation. I was supervising the installation alongside a third-party contractor who was responsible for making sure that the refractory material itself was correctly applied. We had issues with the refractory storage. From the day that I arrived on site, the material was stored in various stores areas around the site, and there was no single consolidated stores log for how much material there was on site at that time, or indeed how much had been used. This was rectified eventually. All the material was brought into a single storage area, catalogued, and we did have the original delivery notices, but they were not accessible at first. Other issues around the refractory installation arose as a result of the high temperatures. We frequently saw temperatures of 30 degrees, if not exceeding 30 degrees, which had the unfortunate side effect of causing the rapid curing of the refractory material. This reduced the amount of time that we had available to work with the material, whilst also, in some extreme cases, being the cause of some rather large stress fractures as the material cured quicker than we had expected. This, thankfully, was rectifiable by the application of a liquid retardant supplied by the third-party contractor, which was mixed with water to cool and thus slow the curing. We also, in cases where cracks had occurred and propagated, we were also able to go back and fill in those cracks with more refractory material. Working on site in India, the primary concern is safety. You can see the picture there is the state of the scaffolding within the refractory at the time of my arrival on site. Unfortunately, in this instance and in many instances, the client is responsible ultimately for erection, and therefore the client is also responsible for site safety measures. The extent of my ability to influence safety on site ends at the point at which I can only request changes to be made to that situation. Several requests were made for the scaffolding to be improved to a more European standard. Unfortunately, these could not be met. However, we were able to make sure that any workers within the cyclone vessel were mandated to wear fall restraints and thus reduce the risk of serious injuries as a result of falling off the insufficient scaffold. Again, temperature was a cause for some concern. Working within that cyclone, the airflow within the cyclone and ventilation is somewhat limited. There's very few man access points, and it is a mostly enclosed vessel. As a result, those high temperatures inside the vessel were exacerbated by the lack of airflow. We did put requests in, and we were eventually granted the use of a large industrial fan, which we used to induce an artificial airflow within the cyclone. And we were also able to make sure that the client provided large water containers on the platform for ready access for the workers inside, so that in the event that they drank their own personal supply of water that they'd brought with them at the start of the shift, they could step outside and replenish that water. Phase 3 was the shutdown and commissioning phase. Primarily, this was split into 3 sub-phases, those being the pre-shutdown preparations, the shutdown itself, and then the post-shutdown recovery. Pre-shutdown preparation for me primarily consisted of ensuring that everything was in place ready for commissioning, and then commissioning as much equipment as I was able to do before the shutdown itself. Unfortunately, when I arrived on site for this period, there were several utilities that were not in place that were required. Requests were put in for them to be, for that oversight to be rectified. The shutdown phase was, when planned, a critical 3-day period in which the existing vessel and mains were to be removed, and then the new mains were to be installed to connect the furnace and wet scrubber to the new cyclone that had been installed prior to this period. This was a construction site at this point, and there was heavy lifting around with all the mains being removed. And so any commissioning that needed to be done during this period, and some did, needed to be carefully monitored and planned around those lifts. And post-shutdown saw me preparing for the furnace to be brought back online, and then waiting until such a time as I could finish the hot commissioning of the cyclone itself. So you can see there a nice picture of one of the cranes that we used. That was the larger 800-ton crane. The lift was planned in 3 parts, as the drawing that I showed at the start showed. We didn't manage that as a result of a number of estimates and calculations for the weight of the mains and cyclone body that were being removed being incorrect by up to 50%. That put the existing inlet main alone, which was the smallest of those lifts, at the limit, the safe working limit of that 800-ton crane, which we can see. That led to the need to recalculate the weight of the plant that was being removed. And then, as a result of that, the lifts and demolition needed to be replanned. So the top of the existing cyclone that was being removed needed to be removed in 2 separate lifts, which induced a delay onto the project, meaning that demolition alone would take 3 days to complete. Now, once demolition was complete, we then had to install the new mains to the connect the vessel to the existing system. This was planned primarily on the basis of a site survey that was made at the request of the client by a client's contractor. That survey was used to establish where we would cut the existing mains to tie in the new mains with the existing system. That was not an accurate survey that was taken out, unfortunately. As a result, the mains were cut in locations that were not ideal for tying in of the new mains, and as a result, we needed to make a few site modifications to correct that and allow the mains to actually be tied in a gas-tight manner. During this period, I found it necessary to commission several pieces of equipment that I hadn't managed to do prior to the shutdown. The pug mill, which we can see in the picture there, and also the nitrogen supply line to instrumentation. So the nitrogen supply line was one of the utilities that wasn't in place when I first arrived on site. Thankfully, when I pointed that out and requested it be put in place, it was done rapidly, which allowed us to then complete the commissioning of those instruments on time. The pug mill, however, did not have a water supply when I arrived on site. Again, it was rapidly installed. However, unfortunately, the contractor responsible was working using an early draft of the drawing, and a key control valve in that supply line was left out as a result, leading to further modifications and corrections being needed. Thankfully, these items were not impinging on the critical times with the delays induced by the errors made during demolition and installation. The small time delay involved with the pug mill commissioning was negligible. So, with the installation finished, the furnace was brought back online, and after some initial setbacks, it was brought to a stable operation period in line with production before the shutdown. Unfortunately, the cyclone radars did begin to show some issues early on. After the stable operation period was achieved, one of the radars began to report a near 100% fill level, whilst the second continued to show a regular, if slow, filling. We determined that later to be a result of the radar branch having been blocked by furnace dust. Ostensibly, the nitrogen purge would be able to rectify that. Unfortunately, there wasn't enough pressure behind that nitrogen purge line with which to achieve the unblocking of that particular branch. After further discussion, when coming back from site, we've supplied a valve to be installed into the radar branch that will prevent the accrual of dust and the blocking of that branch in the future. Unfortunately, these issues couldn't have been predicted and were not known, as Dalby is the first site that we've commissioned radars. So, to conclude, there are issues that were experienced on site. Some of them outside of my ability to control in any other way but mitigation. Safety being one of them. Safety is always an issue in my experience on Indian sites, and all you can do is request that changes be made, and in this instance changes were made. They were not ideal, true, but they were made, and it did improve site safety. Weather, again, was mitigated for as best as we could. Finally, commissioning. Needing to commission in the middle of a construction activity is not ideal by any stretch. As a result, you need to plan properly and work alongside those contractors responsible for the construction to ensure that there is no unnecessary overlap of activities. Despite all of this, JSW Dalby was a successful project. The cyclone was installed, commissioned, and performs in its intended role. Thank you very much for your time. Please, if there are any questions from the judges, feel free to ask.
Okay, thank you very much, James. Alan, would you like to start the questions with a question? You need to unmute yourself first.
Okay, I think I've successfully unmuted myself. So thank you, James, for a very clear and interesting presentation, reminding many of us that the world we have to deal with is the real world rather than the way we might like it to be. You said you had to control a number of things by mitigation, but of course you now have the experience of this installation behind you. So
Yes.
so in future you have the luxury of being able to anticipate rather than mitigate. Could you suggest a couple of things that you would do differently in setting the job up in the first place if you were to revisit something like this in the future?
Okay, yes. So I'm going to answer that one from a safety perspective. I believe that was the angle that you were asking the question from. The issue that we have in situations like this is that the client ultimately is almost always responsible for safety, ultimately, of the site in general. Obviously, we are personally responsible for our own safety and the safety of others around us, but the site safety itself is frequently the client's responsibility. In the future, yes, certainly there is more that we could do, but again, you're relying on the client to implement your suggestions. So yes, in future, it would be possible to request that the client puts things in place beforehand if you know that they're in place, that these issues are there on site. But again, frequently we wouldn't be certain that these issues would arise before we were there on site, at which point it's a case of requesting from the client that they provide the resources to enable you to work safely or in a more safe manner.
Okay, Stuart, would you like to ask the next question?
Yes, thanks, James. Thanks for a nice, clear lecture. I'm not going to ask one single question. I'm going to build up to it. Have you worked in India before?
Yes,
And if
I
so,
have.
did you not expect this kind of system to be in place? Because
This wasn't my first experience working in India. No, I'd worked on a previous site as a junior member of an installation team. Did I expect it to be an issue? I expected issues, yes. Scaffolding is a classic. It's frequently. I was quite happy to have steel scaffold poles rather than bamboo. Yes, I did anticipate issues. The issues that were experienced, I couldn't possibly have realistically known before arriving on site.
when you arrived on site just before the installation was to be renovated. I mean, often with these kind of jobs, you go there a few days beforehand to check it all out.
So
was there no opportunity to do that?
So when I arrived on the site itself, the overall site and construction was overrun by the client. The first time I arrived on site was for the refractory installation period. That was as a result of the client. The refractory itself was a guaranteed item for longevity and performance within the contract. So it required that there be a Primetals and third-party refractory specialist contractor on site to oversee it, to ensure that it was being installed to the correct standards, so that if an issue did arise in the future and the refractory was suboptimal, then we could point out and say, look, well, this wasn't installed per standards, or it was installed per standard because we were there and we saw it, and if it wasn't being done properly, then we would have had them remove it and redo until it was correct. So I suppose I've gone off on a bit of a tangent there to answer your question. I arrived on site prior to the refractory installation period. However, the majority of the work was done without direct supervision from Primetals themselves. So by the time I got there, the cyclone was already constructed. It was already up. It was the lining that was being done inside, and a bit of the peripheral work, putting the instrumentation in place and finishing off a few ducts and branches at that point. So I suppose what I'm trying to say is, yes, the people did visit the site previously. The majority of work and preparation for the work was done without us there. So we wouldn't necessarily know the exact situation on site prior to our arrival, in the event that the client is doing the majority of the work unsupervised.
Okay, Kimberly, do you have a question?
All my questions have been covered by Alan and Stuart there. That's what I was going to ask about the safety aspects. I am curious though as to if there was any resistance from the actual staff that were involved in terms of the safety mitigations that you were wanting to implement.
Yes and no. It depends who you talk to. So their site safety manager, responsible for that area, when it was raised with him, he was very much of the personal mindset that safety is the first concern. The most important thing on site is safety. And my experience is that you will hear that quite often. My other experience is also that, that might not actually be replicated by the workers on site. I think the issue, it's a different
culture.
It is a different culture, yes. Their safety culture is significantly different to ours. So whilst you may get people agreeing that safety is our number one concern, and there's posters all over the site that all make it clear that safety is their number one concern, but the implementation of that isn't always there. So yes, you'd get the managers saying, yes, we'll do that, and then a week later when you say, why haven't you done that, it'll be a case of no time or resources or some other deflection as to the question. And eventually it will be done to a certain level. Like I said, we managed to open up their stores and get fall restraints, which weren't provided to any of them prior to our arrival. But we never did get a decent standard of actual scaffold itself.
Okay.
So out of just a quick follow-up question. So out of the issues that you outlined as being the three main points that were the issues to overcome for the project, which of them do you think was the one that had the biggest impact that you could then control better in the future?
So I'll go through the three of them again. So we had weather, which again is a case of mitigating its effects. Unfortunately, we can't control what the weather does and when it does it, but we can again put fans in place to cool, have water readily available, minimize the amount of time that workers are inside the cyclone as best as we can. One of the biggest problems was that because it needed to be done under supervision and there was only myself and one third-party gentleman there, we couldn't refractory line on successive shifts. So ideally, with the heat being an issue, we would have preferred to probably line it during the evening and night shifts, where the heat is not such an issue. But unfortunately, that's not always possible. Safety, all you can do is request. Invariably, all you can ask is that they, take into account the workers' safety and put systems in place to protect that. And when it came to commissioning, is probably the one that we're most capable of controlling. Beyond, requesting changes be made. So commissioning during an active site, yes, we can definitely mitigate for that. We can work around that. All it needs is proper communication and planning. And if you send an email requesting what equipment you need, making sure that things are in place prior to your arrival on site, then yes, that almost certainly would have helped had I, before I arrived, made sure that my local contact made sure that he had everything in place, such as the water line and the nitrogen line. In the future, I would definitely be more inclined to send an email prior to my arrival and just make sure that everything is there ready for me.
Excellent. Very, very well presented, very clear. Thank you very much. Well done.
Thank you.
Yes. Thank you, James. Thank you very much. Can you stop sharing your screen now, please?
I can indeed. It's just a case of dropping the ball over your name, isn't it?
No, there should be a stop sharing
Right. You mean
somewhere.
okay? Yep. Sorry.
That's it.
There we
Right
go.
now. Thank you very much, James. I'll change the presenting role to Peter now. Right. Are you there, Peter?
I am.
Right. If you could share your screen with us, please. And we'll wait till that's up and running before I start the stopwatch.
Can you see that okay?
Yep, that's okay now. So whenever you're ready, I will start the watch.
Right, okay then. So I'm Peter Taylor and I'm an assistant refractory engineer at Prime Metals. This is my presentation on the impact of checker brick geometry on blast furnace efficiency and the analysis of some concept checker designs that I did. So during the presentation, we'll go through a general understanding of blast furnace and a stove, heat transfer and the benefits of increased hot blast temperature. We'll discuss what a checker brick is and how to design a good checker brick. And then we'll look at the checker brick designs that are produced and compare them. We'll then conclude the presentation. So the first slide is what is a blast furnace? So a blast furnace is essentially a vessel which is used to produce molten iron from 4 ingredients, which are iron ore, fuel, so often coke, some form of flux such as limestone, and hot air. The outputs are iron, molten iron and slag. And so previously we said one of the ingredients is hot air, and that comes from the hot blast stoves. So hot blast stoves, like I say, is used to produce this very hot air which is blasted into the furnace. The intense heat in the hot blast stove is produced on one side, which is the combustion chamber. This heat is then stored within the checker chamber and is later used to blast cold air back through the stove to heat the air before it goes to the furnace. So if we look at these two diagrams, the one on the left is a hot blast stove which has an internal combustion chamber. So you can see here, this is where the burner is. Intense heat would be produced here, which would travel up through the combustion chamber, around the dome and into the checker stack. These checkers would then heat up, and at a later point, cold air would be blasted through here, up through the checkers, back round and out here towards the furnace. That's shown again on here. So again, cold air coming in, down through the combustion chamber and to the furnace. So what are the benefits of an increased hot blast temperature? So of course the main benefit is always going to be cost saving. That's what business is all about, and the cost savings from increased hot blast temperature can be quite severe. So if we can see, by increasing, as a general rule of thumb, by increasing the hot blast temperature by 100 degrees, we can reduce the required amount of coke by 7 to 20 kilos. So just a quick calculation shows that if we increase hot blast by 100 degrees on a 10,000 ton per day furnace and save an average of 14 kilos of coke per ton, with the price of coke being approximately 0.25 euros, would save 35,000 euros a day. And on the other side of that is the more green side of increased hot blast temperature compared to producing that heat within the furnace. So by needing less coke, we're burning less fuel, which is more efficient. It's producing less fumes, less greenhouse gases. It's better for the environment, which obviously is a big thing now. So yeah. Now we'll look at the three different methods of heat transfer. So the first one is conduction, which is the process of heat transferring from two particles coming into direct contact with each other. So if you think like a pan on a stove, or in this instance, the hot air touching the checkers within the stove. The next form of heat transfer is convection, which is the result of fluid motion, such as air passing by cooler air. So there are two types of convection. You've got natural, which is the result of varying densities of fluid. So if you heat a fluid, it becomes less dense as the heat increases. This then rises, displacing the lower density, cooler fluid, which will then heat up, and the pattern continues, causing the flow of air or whatever the fluid may be. The other form is forced convection, which is the same sort of idea, except instead of the densities causing the fluid motion, it will be a fan or something along those lines. The final form of heat transfer is radiation. And this is the result of electromagnetic waves, so light, radiating from the heat source to whatever it's heating up. This doesn't need a medium to travel through, so like the sun heats the earth, it can travel through space where there is nothing between the two. Now, if we look at the three types of heat transfer and the equations involved in these, where I've highlighted, you can see the heating surface area is directly proportional to the rate of heat transfer for each mode of heat transfer. And this takes us on to checker bricks. But what is a checker brick? A checker brick is a medium heat transfer, so it would store the heat and release it at a later point. What makes a good checker brick? So there's four main points for producing a good checker brick. It's the ergonomics, so how easy is it to handle and install. There's no point in having a perfectly efficient brick if you can't install it into the necessary process. The next point is how manufacturable it is. Again, it doesn't matter how great the brick is. If you can't make it, it's a pointless exercise. It's got to be suitable for the manufacturer to produce. The more technical, you've got the cold crushing strength. So the checker brick has a very large stack of bricks above it. If you assume the bottom row, if the bottom bricks aren't strong enough to support all of the bricks above, they will crush. Therefore, they need to have a sufficient cold crushing strength. And the final point is the heat transfer process. So how well the checker brick absorbs and releases heat. Because of the mode of heat transfer, there's got to be sufficient airflow. There has to be a sufficient heating surface area to absorb and release that heat. And then there needs to be sufficient material within the brick to store the heat so that it doesn't just lose heat rapidly. So, as we've just discussed, there's the three main aspects of the geometry of the checker brick, which are flues for the airflow to allow for sufficient flow of air through for the process, sufficient heating surface area to allow the brick to heat up and cool down, well, heat up and release heat at the rate required, and a good enough material volume to store the heat, making it more efficient. So if we then go on to the checker brick design, this is the current, well, it is a current standard checker brick in the iron and steel industry. So you can see it uses 7 flues, 7 centered flues, and around the outside you've got the additionals, which when you stack them up and put them together makes a total of 12. There is a sufficient wall thickness, making it strong enough for the cold crushing strength and heat retention. It's a very basic design, making it very easy to manufacture, and it's a very well-sized brick, so it's easy enough to install. When we go on to the first concept that I produced, it uses the same sort of external shape, but this uses slots rather than the holes. Now, I initially thought having the slots rather than holes would mean I could increase the heating surface area, which would increase the efficiency. But when you look at this brick further, you can see there are some problems, such as the sharp edges and corners, which reduce the manufacturability because of the higher likelihood of causing faults. The exterior castellations increase the surface area even further, but again, they do have some sharper edges, increasing the chance of cracking. Concept 2, same sort of idea, using slots instead of holes, just in a different sort of pattern. Again, had a sufficient heating surface, it had a sufficient material volume, so it had a good enough full crushing strength. It had further increased heating surface area for greater efficiency. Maybe it's a bit more of a complicated design, making it potentially more difficult to manufacture and therefore more costly, but overall greater than concept 1. Concept 3 used kind of combination between the standard and what I was trying to achieve. So with larger holes, again increasing heat and surface area, but reducing the material volume, which potentially would result in a limited heat sink, meaning it would be less efficient. This would be much more manufacturable, though, although if the walls were too thin, that would be difficult for the manufacturer. Concept 4 combined concept 2 and 3, making use of the kind of pattern produced in concept 2, but the more whole kind of flues from concept 3, further increasing the heat and surface area with a more intricate design, which again would potentially be more expensive but acceptable if the financial gain from the overall process was greater. Then the final concept was completely different. It focused around a more square shape, a more simple shape, with much thicker walls, and ignoring the details for the stacking method there, it would be much more simple to make, but with limited heat and surface area. So these were all compared in mathematically and in a weighted matrix. So this is the mathematical comparison showing the various cold crushing strengths of each brick and the heating efficiency of each brick. So for this, I've assumed 62% alumina for every brick and a column height of 50 meters. So you can see the cold crushing strength for all of the concepts was greater, and the heating efficiency of most of the concepts was greater than the standard design. If we move to the weighted matrix, you can see that the efficiency was weighted highly, because that is the main purpose of this exercise, was to create a more efficient design. The strengths are found to be pretty much irrelevant for this task because every brick was sufficiently strong. So I give that a low rating. Manufacturability I considered quite highly. The cost was not as high as manufacturability, but more important than the strength. Ergonomics was rated as lowly as the strength because they were all well sized, so they were all going to be well rated. And the airflow was considered quite an average sort of weighting. So the result of this was that concept 2 and 4 were greater than the standard design, albeit only just. But if we were to examine this further, it would be likely that they weren't quite as good as the standard due to the higher complexity of the bricks and the more likely cost implications of the new designs. Concept 5 was a failure. It did not compete anywhere near where I'd hoped. And concepts 1 and 3 were not as good as the standard, so wouldn't be a viable option. So, to conclude, it's clear that the checker brick has quite an impact on the overall blast furnace efficiency, increasing the improving the cost of running the furnace and offering a much greater profit to the supplier. The hot blast temperature again has quite significant cost implications, and where it's possible, an increased hot blast temperature allows for great cost savings. The concept designs that were produced show that there is the potential to develop a greater design, albeit maybe the concepts that I've produced aren't where we'd like to be, but it does show that we don't necessarily have to stick with the standard design. It could be improved, but at that point, the standard design is still certainly an effective option, and it isn't a disadvantage to still use. So that concludes my presentation. Have you any questions?
Thank you, Peter. Let's start with Kimberly this time for a change.
Hi,
You
Peter.
have a
That was
question?
I do. It was a very interesting presentation. I'm just curious, the data that you had about each of the different concepts. I'm just curious as to how each design was actually tested. What systems did you use to? Was it virtual testing? Was it physical testing? How did you come up with that data for each concept?
So you're on about the heating surface area in particular?
Yeah.
Okay, so the heating surface area, I've calculated a form of efficiency for each one, which is the heating surface area over the volume, over the number of checker bricks within 1 meter cubed. So it gives me heating surface area per meter cubed of bricks. So it hasn't been tested specifically on a computer program. It's more of just an Excel calculation. If that answers your question.
Yeah, it does. So at the end there, when you were summarising, you said about there may be alternative designs that could be looked at and more improvements could be made. So what alternative testing methods, like using software, can you foresee in the future to maybe be able to improve the design even further?
Okay, so we could use some sort of 3D analysis. So FEA, I believe, would work, if I'm remembering correctly from uni.
Yeah.
So we could model these concepts rather than just having a written calculation. If we had the sufficient computing power as well, because obviously having a full stack of checkers would be quite tasking for the computer.
Yes.
So if we were to be able to model the full stack, we could run a program to determine the actual heating surface, well, not the heat surface area, but the heat sink, and how much heat is lost and gained, and essentially the benefits of the different concepts. So yeah, because of the time constraints of this project, I didn't use any sort of advanced methods to determine which was the better concept. So it is using the 2D analysis. Yeah, so I think does that answer the question?
Yeah, it does. That's brilliant. Thank you very much, Peter.
Thank you, Peter. Alan, would you like to go next? You're still on mute, Alan.
Sorry, I think Kimberly gets her own back this time because she's asked the question that I wanted to ask. Thank you for the presentation. It was clear and it was very interesting. You have a number of factors that you consider in this design study. There's the geometry, there's the gas flow, there's the materials, etc. We've just heard you answer the question about the heating efficiency and the effects of surface areas. Could you say a little bit about the considerations around the materials and what would cause a checker brick to fail when it comes to the end of its life in service, and how do you take that into account in your analysis?
Well, to be honest, I haven't taken the end life of the checker brick into the analysis. But for the material side of it, it would be dependent on the stove temperature that we'd look at running at. So obviously it wouldn't be just as simple as saying we'll stick 62% alumina throughout the stove, because we've got to consider the cost and the efficiency of 62% alumina. Again, there would be further materials we could look into. I did look further into the different materials, but to be honest, for the sake of keeping this presentation within a reasonable time frame, I didn't go into that sort of detail. But yeah, so we could look at the various materials, but from my experience, we predominantly use alumina for checkers. We have used silica, but silica again has more issues. It's a lot more temperamental to heat. But yeah, so from my analysis, I only really did it on the various sort of alumina materials. And because of the purpose of the project being to analyze the geometry, there was no sort of rate of research into a different material to what I was used to. Don't know if that fully answers what you're asking.
I think it gives us a good idea, so thank you.
And Stuart, would you like to ask the last question?
Yes, thanks very much, Peter. That was a nice presentation. I've got a very basic question, really. Did you do a literature survey before you embarked on this? I mean, this is not new. This is quite an old technology. Goes back several centuries, and modern designs of units include a whole range of different sizes for checker brick. You've got 12 hole, which you used as your basic design. There's 19, 32. It goes on and on. So there's lots of different designs for checker bricks. Lots of information in the literature, and different shapes and sizes are all included. So did you look at all this stuff before you started on your exercise?
So the honest answer there is I had a brief overview of what was available. But generally I kept it within the iron and steel market, so I didn't look outside of what would kind of be the norm for us. So I did look at almost the history of checker bricks. Now, when I looked online, I found it very difficult to really find much other than companies trying to sell me them. And generally speaking, they were often the same sort of hexagonal shape. I did find some square bricks, which is where concept 5 came from, trying to advance what I believe was from the 1800s of the design that I found. So to answer the question, yeah, I did have a look at what was available and try to compare what was on the market. But of course, it would be possible for me to look into greater detail onto that. But I certainly didn't find anything that kind of replicated the sort of slot designs that I was going for.
Okay, does that answer your question, Stuart?
That's fine, thank you.
Okay, well, thank you very much, and thank you to both of our contestants. I'd like to thank everybody for coming to support our contestants. We've had an attendance of 39, which is a very good attendance. I'll close this part of the proceedings now, and judges, if you'd like to be totting up your scores, please, I'll open the private meeting between the four of us in 5 minutes or so. So thank you everybody for attending. If you'd like to come to some of our future events, please feel free. Steve Pallant and Denise Dowson are always aware of what our next event is, and both of them have my contact details if you're from Primetals. So it only remains for me to say thank you and cheerio, everybody. I hope to see you again soon. Bye-bye now.